So yeah, I used a BuzzFeed title here, but I forgot to do a control talk to see how the crowds turned out. So I don't know if this is actually effective. But in any case, if you don't know what these wooden nesting dolls I'm referring to are, they're Matryoshkas, Russian nesting, right? Stacking dolls. You get a bunch of them. And so I use this as a metaphor for recursion. So there's a Matryoshka library written by me and other people at my company, SlamData, or the company I work at. And then this talk is all available at this repository, and there's other versions of this talk from conferences I've spoken at before, also there. So I've been talking about this recursion scheme stuff for this year a lot. And what it's about is basically separation of concerns, which you may have heard mentioned in other contexts as well. In this case, it's separating recursion from all your business logic and stuff like that. And so you don't implement recursive functions all the time. You basically defer to this library to add recursion to your programs. So we talk about how to do that. The name Matryoshka is meant to invoke the idea of finite nesting, right? There's only like 7 or 8 of these dolls that stack up. You don't have infinite recursion and stack overflows and stuff like that. The idea is that it models a finite terminating recursion. However, there is a dual to that, which is co-induction. So induction and co-induction, which if you were at John DeGoza's talk yesterday, you might have heard some stuff about that. And that is basically a way of modeling infinite recursion in a way that is productive, where you're producing something at every step and also avoids, it's a way of modeling event loops without worrying about things like stack overflows and things like that. So Matryoshka models both of these versions of recursion and co-recursion. So recursion schemes is a pretty big topic. The library itself implements some portion of that and is increasing in how much it implements. This talk talks about a fairly small piece of Matryoshka. And oh, I'm too far away from the mic? Yeah, sorry. So is this good? Yeah. OK. So yeah, Matryoshka implements a small or some portion of recursion schemes and is growing in what it implements. This talk kind of covers a small part of that and also a bit of, if we get to it, the future of where Matryoshka will grow to, but isn't yet covered. And then tomorrow, Rob Norris is giving a talk that uses recursion schemes in some database stuff that he's working on, and he has a really great motivating example and stuff. I really encourage people to see that. And so yeah, so that's kind of what I'm covering here. I always forget this part, so I wanted to put it up front. I didn't invent any of this stuff. This is like me reading papers and talking to people and stuff, and this is sort of a list of the biggest influences. Ed Komet and Patrick Barr both have very good Haskell versions of recursion schemes implemented. Patrick Thompson has written a bunch of introductory blog posts and explanations and also given some talks on recursion schemes that are very helpful. There's a ton of papers on recursion schemes. 2 of the biggest ones are this functional program with bananas, lenses, envelopes, and barbed wire, which these are not the lenses of optics, if you're familiar with optics. It's just specific to recursion schemes. And that's by Eric Meyer and others. And then finally, Typelevel, which this is a Typelevel incubator project. The Typelevel community has been awesome, and they're very supportive and very explanatory. They're happy to discuss things and tell you, or explain how to approach different problems. And a lot of this wouldn't have been possible without learning from various people there about how to solve different things I ran into. So I want to shout out to them. So we'll start here with a simple AST. And this is a recursive AST. You can see here, so it's this expression, right? This abstract class expression. And in one of its case classes that extends it, it refers to itself, right? So you're basically creating a recursive structure here with some number of multiplications containing numbers at the leaves, right, of this tree of operations. And you might have some evaluation function that takes your expression and then returns an int, right? Evaluates that thing. If you hit a number node, it just returns that value. If you hit a multiplication node, it recursively calls evaluate on each of the 2 arguments to that. Does that make sense? That's the kind of starting point for all this stuff. From here, what I mentioned is what we want to do is separate recursion from our code. So we don't have to think about recursion and things we do. There's a great talk by Stephen Compall called add a type parameter, and that's what we're going to do here. So we add a type parameter. And so now where we previously had recursively referred to expr in these cases, we now just refer to a, our new type parameter, right? So we have an expr a, which is now a functor. And num doesn't actually use a, it just still has its int. But in the recursive cases, we're now referring to a, right? And so here's our new evaluator, although it's kind of odd. It just says like, oh, well, if the a is an int, we can just like, just multiply those ints. But I mean, how do we end up with with your a being an int? We want some recursive structure here. We don't want to. So we'll figure out how we can get to a point where this is actually implementable. So we have to reintroduce recursion somehow, right? We've pulled it out now of our data structure, but how do we say we want to use something in a recursive context? You say, well, previously that a was just expr, so we can just expr of expr. Well, that doesn't work because expr takes a type parameter, and so you end up an expr of expr of expr of expr of expr, just recursively, right? Now this actually would work if you wanted to make something that was no more than 5 levels deep, right? Just like as long as it fits within those first 5 levels, you can write your expr. And if you wanted to have one 4 levels, or you could actually have it no more than this, and it would still, as long as you hit with the leaf nodes, it would terminate anything up to 5 levels deep. But of course, this stuff isn't really what we're trying to get to. So there's this nice little type called fix, which itself is recursive. And this is basically like the Y Combinator, but applied at the type level. So basically fix of some functor, which in our case was expr, right? So fix of expr holds a value that is a expr containing recursively a fix of expr. So this is your way of tying that knot of saying expr of expr of expr of expr of expr as deeply as I need, right? Without having to be explicit about that level of depth or anything. So now we have this type that tells us that we have a recursive structure here of exprs, and that's what this is indicating. So I mentioned fix. There's 2 other ones. I'll use all 3 of them in the talk as I go through. Fix is defined as I showed here, very very simply, very directly. I feel like it's really good for explanation. Mu and nu are more complicated definitions, but they're meant to model explicitly the inductive and co-inductive data structures that I mentioned before. So like finite structures like a list, and then nu would model potentially infinite structures like a stream, things like that. So depending on which of these things you use, you kind of have different performance and behavioral properties. But again, you can like kind of put them all in the same position. You could have fix of expr, mu of expr, nu of expr, and it does change some ways in how they behave in recursive situations, but they all represent a recursive structure of expr in that case. So since we have a bunch of them, we'll make a type class, right? And so now we can say like, oh, okay, all these things can have the same behaviors. We can define that type class. The type class is for some type, and so I have an instance here to show you with fix. For some type, fix of f, there is what's called the base or pattern functor. In the case of these types, that's just actually f itself, right? So fix of f, and if you actually had a fix of expr, your base would be expr in that case. And then there's a single operation you have to implement, abstract def, which is project, which basically takes your recursive structure and unwraps one level. So now what you have is that expr, right, which is the structure you'd like to think about, containing recursive exprs, right? So this project basically unwraps it from that structure. And in the case of fix, I can go back to see here, fix just has a field unfix, which is that structure. So it's very simply just access the data that fix is holding. And again, with mu and nu, it's a little more complicated, but they do effectively the same thing. They all can implement this project. And now, so this can really model basically any recursive structure. You can see we basically here, we re-implement lists, right? So we define a functor for lists, just as we did one for expr, right? So normally list takes 1 type parameter. Now it takes 2, b being the recursive one. So in the case of nil, you don't use either of them. But in the case of cons, instead of the tail being list of a, since it's recursive, you just use that recursive type parameter there for your tail. So you actually now just have two type parameters. You can either get the head of A, which is A, or the tail, which is B. And so now the type list is isomorphic to this mu of the list functor. And this other type, colist, the dual of list, is new. As I mentioned, the mu is inductive and the nu is co-inductive, so potentially infinite. So this is how you model a stream. There's a reason I didn't call it stream. I'll get to that in a little bit. But this is the common kind of model of stream, right, where you can have a potentially infinite list effectively. But again, notice that like there's just the one functor. When you define type classes on this functor, like by traverse or other type classes, you get to take advantage of those as if you had done both of these data types, right? You don't have to re-implement everything for stream that you had implemented for list or anything like that. You basically just say, oh, I want this structure to be potentially infinite in this context. So you get to defer that decision as to like what is the shape of this basically, or what is the behavior of this until you actually need it, with only defining this one shared functor. But it turns out you don't actually have to replicate lists. You can actually define a recursive instance of this recursive type class on list directly. So you can just say that list of A, right, is recursive. You still have to tell it what the functor is, and that's actually why it's defined in this particular way. With the fixed point types before, I went back too far. With the fixed point types before, it seems kind of silly to not just make, at least I thought so initially, to not just make recursive take this fixed type and not have an f here, and just make the f happen in the operations as a type parameter at this level. But the problem is when you start dealing with things like lists or co-free or other data structures, that no longer holds. So here in the case of list A, or of list, you have to say that the functor is this list f, which you clearly can't just like automatically derive from this type. Or I mean like you couldn't do a type class where you had like some list that takes some parameters and then that parameter is filled by list f. So anyway, here you've mapped, this is your recursive type, and you say like, okay, the functor for it is this. And then again, you just have to define project, which maps the nodes of a normal list to your functors. So now you have an instance of list being a recursive structure, right? There's actually basically, like I mentioned before, basically any recursive structure. There's the three true fixed point ones that are that just take some arbitrary functor. List and colist, as I mentioned, both use list f as their functor. And this is why I didn't call it stream. So stream here, its functor is just a tuple. So this is like, just think of where this question mark is. This uses kind projector if people are familiar for, yes?
What is exactly the implementation of mu and nu?
I can show you the implementation of mu and nu.
You showed fixed.
Yes, because that one's easy to show.
Is there a difference between these three somehow?
Yeah, there is. Here, let's see here. Make this a little bit bigger. So here you can see mu. It's again a case class, and it takes this what's called an algebra. So it is basically implemented as a fold itself. And so this is the mu structure, and then the nu structure. Oops, hold on a sec. There you go. The nu structure, which I also make. Is very similar, but instead of taking an algebra structure, so this is just I'll just add a comment here that says that this is actually a function from A to f of A. This is what's called a coalgebra, and so nu is defined using this coalgebra as its basis.
So they're actually quite different.
Yeah, they are very, very different. Yeah, yeah.
But if the base functor had some properties, then wouldn't you have to redefine them for the fixed points in all the three different cases?
No, you don't. So in the library, you'll see there's a bunch of sort of for free type classes you get when you have some recursive instance, and then when the base functor on it has bi-traverse or bifoldable or monad or other things like that. So just by the combination of your type classes on the functor and type classes, the recursive type class, those properties fall out. And I am happy to take questions during the talk, so I'm glad somebody did. A couple people have, and yeah. I was getting to stream here. And And so I mentioned that the question marks are from kind projector. This is basically like a partially applied type, right? We're just saying we're turning this into a functor of a type constructor of one parameter by specifying one, but not specifying the other, which is what the shape that all these have to have. So in the case of stream, the functor is just a tuple, where A is the value type of the stream, and then the question mark is, or can be represented by recursive versions of this same structure, right? So you basically just get A. So the difference between I'll call it a true stream and colist is this is always infinite. It has no end, right? It will just continue to generate values indefinitely, whereas colist can be terminated. And that's why I made that distinction earlier, not calling this stream, although stream is the commonly used terminology for it. Other structures, I thought I eliminated all mentions of free and co-free from my talk, Rob, but apparently this stayed in there. So this is the environment transformer comonad. And this turns out, it's a useful type on its own, but it turns out to be the pattern functor for co-free, free, which is the dual of co-free. Nat, right, so just a natural number, turns out is just the fixed point of option. None is 0, and sum is, successor. And then for any arbitrary type, you can get a functor from it just using const. And so you can get, if for some reason you want to use some non-actually recursive type in a context where you need a recursive type, you can take advantage of this instance.
Hey, I'm sorry to bother you again, but you just got a little battery warning.
Oh, I'm not plugged in. There is a plug. Thank you for that. All right. So that recursive type class I showed you, we had one. Yeah, there's an instance of it here, right? Where we define the project, it has a dual, so we reverse the arrows, right? Miles. In its dual, it also has the same base functor. In the actual library, this functor is pulled out into its own super class of co-recursive and recursive. I don't know if it's worth actually keeping it that way, but it is some shared aspect of the two. And then the dual of project, which unwraps one level, is this embed operation, which takes, I'll look at the implementation because the implementation for fix is often clearer than the type class specification. So it takes some unwrapped one, right, where you have say expr of fix of expr, and it wraps it back up. So you go back to that recursive structure. So that's the dual of, and this type class is the dual of recursive. So we'll see that everything that you can do with the recursive type class has some corresponding operation in the co-recursive type class. So what kind of thing can we do with this? So here's one of the other operations in that type class, which is already implemented, although some of the instances like mu and nu override it to take advantage of their particular structures. But a catamorphism is a fold, which basically takes a function from some functor of A to A, which you'll notice matches the evaluation thing we showed earlier, an expr of int to int, where we basically assume that the nodes of the recursive things are not actually recursive, but just have already calculated values in them. And so we only have to calculate one level here. And so it basically takes a function of this shape and applies it across an entire recursive structure. So you can go from t can be fix of f, and it applies the recursion for you, and so you get the final a value, which in this case would be int. And the way it works is it basically takes your recursive structure, does the project, unwraps it one level, right? Then recursively calls itself, so it basically just goes all the way through your tree, unwrapping one level, one level, one level, and then finally, and then once it's done, each call returns applying this operation. So when you're actually at the leaf nodes of num, right? That's like a terminating case. You just get the int back, and then now you have ints in those places where you call mul. We can see, I think, here as an example of like here's some recursive structure, right? So it'll traverse through pop, 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 like unwrapping all those things, projecting them all out. Then when it hits a num, it'll just replace that with 2, replace that with 2, with 2, with 3, and then it'll say, okay, now I have a mul with just an int 2 and an int 3. It'll turn that into a 6, and so on, and eventually it'll evaluate to 48, applying that recursion through your whole system. There's this dual notion, anamorphism, which does the opposite. It takes some value and recursively applies the dual of the opposite of this, right? Where this is f of a to a, this is a to f of a. And so it applies that repeatedly to this single value to get some recursive structure. So we'll see that here, where you can say call Anna with some function that says like does prime factorization, which whenever you hit like say if you hit a composite number, it just somehow breaks it down into 2 components, and it will continue to break those down recursively, and you would end up with some kind of tree sort of like this, where you see like at the end you end up with mole of num, mole of num, mole of num, mole of num, and num, right? And so you would have your now recursive tree that would have all that stuff. So you can build recursive structures from seed values. And here's the implementation of fold right using this. So kata is a generalization of fold right. You think of foldable as a generalization of, as a generalization of like kind of fold right on lists. But actually what foldable does is it makes you think of your data structure as a list, right? It throws away all the other information in your data structure. Whereas this allows you to say like, well, depending on what the actual shape is, I can do different things. So if you do a catamorphism, as we did here on with the evaluation, you're matching on num and mole. It's not just like you have one piece at a time. You can do arbitrary complex things related to your data structure. So this gets more generalized. All this stuff can be Kleislied. I'm not going to mention that. Rob talks a little bit about that stuff. Because recursion is not always simple, right? You often want to like short circuit or do other things. I'm almost out of time, so I just want to, I won't go too much into details, but basically all of your folds, all the recursive operations can be generalized over some comonad. In this case, a tuple that carries the original structure with it as you fold. So you can always look back and use deeper parts of the original structure to inform the decisions you're making now. And again, all these things have a dual. So whereas in the folds, you have an arbitrary comonad, in the unfolds, you have an arbitrary monad. And so in this case, we have a disjunction where when you're unfolding, you can decide that when you hit a certain point, I don't want to keep recursing down that structure. I just want to say like, oh, here's the rest of this branch right now. Just recurse over the other branches from this thing, but this branch is now done. And so that's what this particular thing is. But again, it can be generalized to arbitrary monad and comonad. So there's lots of variation in what the behavior you can get out of this. So here is a cheat sheet, which I don't expect anybody to actually look at. But this is some of the more popular ones in their names. Because before people actually generalized it, they were like, oh, here's one case. Oh, here's one case. And then somebody noticed a pattern and said, like, oh, we can just generalize these. But there's a lot of them. And there's tons of different variations you get like that. I have to switch back to this. So yeah, there's a ton of benefits you get from this. Like so, as Patrick Thompson paraphrased, his paraphrase is much better than the original. He says, myriad all go so far as to condemn functional programming without recursion schemes as morally equivalent to imperative programming with GOTO. So hopefully that chastises everybody into looking into separating the recursion from their business logic. It might be a little strong. I feel like there's still a lot of cases where it's not obvious how to map these things, although there's always more research in this stuff. You can do interesting stuff like annotating arbitrary trees without having to create new structures. Rob will talk about that in his talk tomorrow, I think. Right? And then some other benefits you get is these structures, these algebras, are composable in various ways. Like you can zip them together, right? So you have one algebra that evaluates and one that like pretty prints whatever your language or structure is, and you can zip them. And so now you do one traversal of your data structure, right? One traversal, and it gives you both values back. So you don't have to do multiple passes over your data. And there's composition. You can apply these things one after the other. Whereas the anamorphism applies things kind of from the base until you get to leaf nodes, and then like wraps that as you go. And then you can unwrap and then apply some fold to get some b value. You actually get what's called a fusion, where there's an operation like this where you never actually build a recursive data structure in the middle. It can apply one operation, basically pulling apart your pieces, and then a separate operation folding it back down without ever building that intermediate structure. So you can these compose very efficiently, and you can get some good performance gains of doing that. So the next step, which I do not think I have time to really cover, is mutual recursion, which lets you not just have a single, say, functor that like, oh, here I can have any of these nodes, any of these nodes. It allows you to use GADTs to categorize and say, like, in this particular context, I can only have a node that has type int, and so like in the add node. And you can see here, const has type int, and add also has type int in this position. And so basically, only those nodes could be used in this position here. Whereas like this one requires a tuple one, which is generated by this pair thing at this point. has that same tuple shape. So basically, this allows you to restrict and use different pieces. So I won't get into the future work stuff. But yeah, any questions?